Welcome everybody. Today we have David Alfaya as a speaker present here at the faculty, so it's our pleasure that we have him here among us. And he's going to talk about some computational tools for exploring the geometry of moduli spaces.
Thank you very much, Marina, and thank you for inviting me to give this talk. As Marina said, I'm going to discuss a little bit about this computational approach for the study of modular spaces. This comes from several joint works with a couple of students, Sergio Herrero and Daniel Sanchez, also together with Javier Rodrigo, Jaime Picoso, and Jose Portela. Also, there will be some results based on, where I will comment about some results based on my thesis with Tomás Gómez, and I will briefly discuss one current work with another of my students, Jacobo Manús, and also with Tomás Gómez. And this is part of an ongoing project, which is a CMOD project, in which we are trying to apply these computational tools and AI to the study of modular problems. The key idea here, or the main idea, is that in some of these modular spaces, there are some combinatorial explosion in the setup for the modular problem. Like, for instance, either the equations for some motivic theories on the moduli are essentially very big expressions that are unable, that are untractable for humans, or, for instance, the stability conditions for a certain modular space become very complicated, and you get very complex stability spaces and very complex stability chamber partitions of the spaces. Some number theoretical results become very complex to do by hand in some cases. And in all these situations, we thought that maybe some computational aid could help. So then we started trying to hybridize an experimental computational approach together with the more classical algebra geometrical approaches. And this is what I'm going to present today. After a couple of years working on this strategy, we have developed two tools that are general purpose tools that I want to present to you, that are meant to be used for the study of several types of problems in modular spaces. So today I'm going to discuss first what we call polypart, and then what we call motifs. These are two Python packages that are available in pip. They're also available in GitHub. You can download them, play with them, try to use them, and in principle, they are out-of-the-box tools. So you just pip install them, and then you can play with them. So I'm gonna first discuss a little bit about polypart. This tool, these tools have a general purpose part and a modular specific part in both cases. So the general purpose part, this is a computational tool for studying partitions of polygons. So you have a polygon in d dimensions partitioned by a generic set of hyperplanes, and then you want to classify, enumerate all possible chambers that appear when you cut this polygon through this set of cuts. The thing is that even if you have very few hyperplanes cutting the polytope, if the cut is generic, the number of walls appearing here, the number of chambers that the polytope gets divided into can rise very fast with the number of planes. And if the number of planes is big, then the number of hyperplanes gives you an exponential bound on the number of chambers, and this is something that might grow out of hand for human tractable manipulation. So what this algorithm or what this package does is it gives you a full, complete classification of them. So if you have a polytope and you have a set of planes, I want to generate these planes, then this algorithm will give you a classifier such that if you give, first, it will give you a full enumeration of all the possible chambers this gets divided into, and second, it will give you a classifier so that if you give an arbitrary point in the space, it will tell you exactly which class it belongs. So what's the application for modular in this case? Stability chamber analysis. Modular spaces, I'm going to discuss a couple of particular examples in a moment, but modular spaces usually get some stability condition associated with them, and these stability conditions form some stability space that very often take the form of a certain point. And then you have walls establishing stability changes in the space. And then you want to see how many of the chambers of these spaces are what we call stability chambers and correspond to isomorphism classes of modular spaces. So then if you want to fully classify all possible different modular spaces for a given problem, you want to classify all possible chambers here. And this is what this does. You give it a modular problem with a chamber description, you give it a wall description, and this gives you the full classification fully automatically. Moreover, it's able to take into account the possibility that there are some automorphisms, some nontrivial isomorphisms between chambers, and it factors out to obtain actual isomorphism classes and actual automorphisms of the group, and compute everything automatically. Let me go even more concrete on this. To be more precise on what I mean as stability chambers and that, let me start from scratch. What's a modular space? A modular space is a type of geometric object. We can see different categories, but typically for this talk, we're going to speak about the algebraic categories, so we're going to think about the scheme. M, whose points parameterize some classification space. So for instance, we could think of, we want to consider algebraic curves, then we can consider a modular space of algebraic curves. And the key point is that we have a classification problem here. We want to classify isomorphism classes of curves. And then we have a manifold, or a scheme, or a stack. And we have a certain equivalence between points in the object and equivalence classes in my equivalence problem, classification problem. And more generally, if I have some notion of what a family of objects is, what do I mean by a family of curves or a family of bundles, for instance, and these are parameterized by some space T, then I have a correspondence, because if I have some algebraic variety representing my classification problem, then a family of objects parameterized by T should be something like a path parameterized by T in my variety. So then I have a natural correspondence between considering families parameterized by T and maps from T to this object in a sense. I'm being a little bit loose here. I'm not being completely formal, but this is more or less the idea. The thing is that when you treat certain types of modular spaces, like for instance, modular space of vector bundles, you cannot aim to obtain a full scheme parameterizing all possible vector bundles, for instance. Usually what you have to do is you have to consider some stability condition and restrict your problem to considering only stable objects in a certain way. So what happens usually is that this stability condition is not unique, but rather it depends on the choice of some stability parameters. So you fix the parameters, then that defines stability condition. But when you move them around, you get different modular spaces. So usually what you have is a stability space, delta, and the geometry of the modular space depends on the parameters. So what you get is a modular scheme depending on this parameter alpha. This alpha belongs to the stability space delta. And then when you move around in delta, you obtain different classes of modular space, different isomorphism classes. And usually what happens is that you get some type of word crossing condition. So the thing is that this space, the change is not continuous, but rather what you get are a certain set of walls dividing your space. If you keep your movement inside one of these without crossing any walls, then you are restrained by what we usually call stability chamber. And if you move around the chamber, then the modular space doesn't effectively change. You get equivalent stability conditions. So your objects, the objects that are isomorphic, sorry, the objects that are stable for one point are stable for another. So you are not changing your class, your moduli. But then when you cross a wall, you change your stability conditions. Therefore, you change the geometry of the moduli typically. And then, well, at the end, classifying these objects do not correspond really to classifying stability conditions, but rather non-equivalent stability conditions. In other words, stability chambers inside this space. Moreover, in modular spaces, like for instance, modular space of parabolic vector bundles, quiver bundles, chain bundles, configuration spaces of many types, what happens is that this stability space satisfies those properties that are key for our setup. One is that the stability conditions, stability space, global stability space, is a certain pointer, maybe an open pointer, but usually it's a closed pointer even. And stability walls are hyperplanes cutting the body. And then in this condition, we can go back to what polypart does. Polypart takes a polytope, takes a set of hyperplanes, dividing it, and then you can obtain all possible chambers in it and the chamber structure. So then this is where we can apply this. And then we can use this computational tool to explore the structure of these things and take some conditions, extract data, and then identify patterns that might not be tractable to find by human knowledge, because these partitions usually explode combinatorially. And then it is very complex to see some patterns in the structure because we cannot experiment with them. What happens usually is that you start with very few cases that you can track by hand, but then these are not meaningful enough or big enough to represent what's actually happening with the data. And then using these tools, we can actually track them. Let me go to a particular example in which we have applied this technique to showcase how we can apply completely this technique to a natural problem, natural order problem in modular theory. So let's suppose you get a real surface and a set of points on them, and consider the modular space of parabolic bundles. So parabolic vector bundle is a bundle on the curve x together with a weighted flag over its parabolic point. So we get on each parabolic point x in this divisor d, you get a filtration by subspaces of the fiber, and then these subspaces have associated weights, each one corresponding to each jump. Usually in this talk, we will consider is that this filtration is full flag, so we have exactly the same number of steps as the rank of the bundle, and therefore there are exactly R weights here. In this situation, you can consider a stability condition depending on the degree of the bundle and the rank of the bundle and the parabolic weights. The parabolic degree of a parabolic vector bundle is defined as the degree of the underlying bundle plus a sum of the weights multiplied by the corresponding sizes of the jump of this filtration. Now, when this is full flag, this is just 1, so that is just a sum of the weights. And when you divide this by the rank, you get what's called the parabolic slope. If you get a sub-bundle, you get an induced filtration by it, and then you can compare for each parabolic vector bundle what's this parabolic slope of the bundle with what's the parabolic slope of the sub-objects of this bundle. That means the sub-parabolic bundles. And we say that a parabolic vector bundle is semi-stable if you have this type of inequality. This particular form is not so important. What's important, or what would be important for us to apply the set that I described before, is that when you unravel this inequality, you get something that is very simple. The slope of a parabolic vector bundle is the degree plus the sum of the weights. You have a sub-bundle, then the slope of this sub-bundle will be some degree of this sub-bundle d prime, of some rank r prime, and you get some selection of weights corresponding to the sub-filtration that you get in this sub-bundle. And then we say that the parabolic vector bundle is semi-stable if you have an inequality between these two parts. Now, what happens is that, in general, if you choose appropriately these weights alpha, then here you can never achieve equality. You can only achieve equalities if certain numerical conditions are satisfied, namely, if the alphas belong to this hyperplane, which is hyperplane with integer coefficients, and whose independent term belongs to some multiple of the rank, up to this other condition. This difference must be an integer. So what happens if we consider, so then this is the stability conditions. The stability condition corresponds, or the change in the stability conditions happen when you cross one of these hyperplanes. If you move around alpha without ever crossing one of these, what we will call walls, then stability conditions are equivalent. Therefore, the modular spaces do not change. So at the end, we have a stability space, which is this product of simplices, in which you have the parabolic weights, which are ordered for each parabolic point. This is part of a hypercube of size 1. And then inside it, you have first these inequalities from a polytope, which as I say, it's a product of simplices. And this polytope is cut down by these stability walls, which are hyperplanes. So then we are in the perfect setup for polypart to act. Then the thing is that, sorry, this is not, sorry. Okay, good. Then you can prove that actually, because in principle, these are theoretical, what we call numerical walls. These walls depend on a possible R, R prime, D, and D prime. But the existence of this R prime, D prime, and these possible choices of the subweights correspond to the possible existence or the potential existence of a subbundle satisfying this equality. But even if you have the numerical condition ready for it to exist, there might not be an actual bundle satisfying this equality. Because one thing is that numerically, you can put here the numbers, select some alphas and obtain the equality. Another thing would be if there's actually a bundle corresponding to those choices. And the thing is that if the genus of the curve is high enough, you can actually prove that this always the case. So then you can prove that the moduli spaces, so every parabolic stability wall, which is numerical stability wall, actually becomes a geometrical stability wall. That means that if you actually go through one of these numerical walls, you can always find a subbundle making or realizing that equality that we find, and therefore making an actual change in stability from one wall to the other. Therefore, we can prove that the numerical stability conditions actually represent the possible chamber, so geometric stability chambers, and therefore classifying the geometric stability chambers is the same as classifying the different numerically. I mean, is the same as classifying the stability conditions from the modulus parabolic functions. Then you can actually find a numerical invariant, which is given by this evaluation of these hyperplanes. So it's like the distance to these hyperplanes in a sense. And these numerical invariants, which are integral, the integral part of the floor part of these quotients, become a vector of integers. And then what happens is that you can prove simply numerically that two chambers are the same if and only if these very big vectors of integers are exactly the same. This gives you a numerical condition for equality of chambers. The problem is that these vectors of integers, given by just the numerical condition, are super big. They rise, the size of these elements rise hyper-exponentially. Because at some point you need to check every possible way to partition into a certain number of choices of weights of rank R prime, and then you need to sum up that with respect to R prime. This rises very fast. So,
sorry, can you explain again what is this distance?
Yes, when you consider this equality, if you get weights alpha I arbitrary outside of a wall, then you know that this difference, if it's not an equality, depends on if I move here R to the left and I divide everything by R, you get an integer d prime corresponding to the degree, right? And even if if I change alpha slightly and it doesn't belong to an integral multiple of d prime, then it must be between two different integral d primes. So given fixed alphas and fixed R prime and fixed choices of what weights to select or which weights not to select, then this thing becomes, when you divide by R, becomes something that is between two integers. So if you get the floor effect, all possible choices of alphas that belong to that band will yield the same difference. So then, unless you cross one of these integer values, then all the stability conditions are the same because the inequalities will always be in the same direction. Only when you cross through an equality and you actually get an integral value is when you have a crossing, because you have some choices for which the inequality went in some direction. Then when you cross through them, the inequality reverts and goes in the opposite direction. So therefore, if you just restrict yourself, you quotient here by R, and you look at the integral d prime that you get, in general, you will never get an integral d prime, but you will be between two values of d prime. Then you can move around as you wish in those integral values, as long as you don't cross one. So then you form a band. You get one integral value for d prime, the other integral value for d prime, and in the middle, even if you move the alphas, you will never cross this type of wall. So then how do you divide in walls? You form these bands for every possible choice of the R and the choices and the R prime and the D, etc., and then those forms bands. If you do not move, if you are always moving inside all of the bands, each band is represented by an integer. You choose the invariants and you choose the corresponding integer to measure the corresponding integer. If two weights belong to the same band for each choice of the representatives and each choice of the R prime, etc., that means that you can go from one to another without crossing any stability wall. Therefore, they belong to the same parabolic. Well, what you can prove is actually that this is an equal. So, okay, this is good news because that means that the computation of stability chambers is fully computable. The problem is that this is not so easy. Why is that? Okay, let me give you an example. If you have n equals 2 parabolic points and rank equal 2, then you have a very simple chamber decomposition. This is, by the way, this has been done numerically just by putting alphas and measuring these vectors of integers and seeing if they are the same or not. You can see very clearly that there's one parabolic wall. This is for degree 0, this is for degree 1 of the bundle. And then you get two different chambers. If you go for one parabolic point rank 3, it's also very simple. You get two chambers, and two chambers. If you go to degree, to rank 3, and you get d equals 0, 1, 2, or 3. Then you can see here that you get 4 different chambers in each case. This is very simple still. And for 3 points and rank 2, you get 5 chambers in each case. This is a little more complicated to be seen, but it's a cube, a unit cube. And then here you get the embedded regular tetrahedron, the embedded simplex. And then you can either position it with the vertex going to 0, 0, 0 or to 1, 1, 1. And you get the intermediate simplex and around 4 chambers surrounding it, completing the cube.
The coordinates are
the weights. The weights. These are 3. Here we have 3 parabolic points. You have one relevant weight for each one of them, and then you get 3 coordinates. Okay. But here's the catch.
The larger they are, the more complicated the picture.
That's the thing. And much more complicated the picture. I'm gonna get to that in a second because this seems nice, but first of all, so even if we get this separation into classes, there's still another problem, which is that maybe I know that when I change from this red class, for instance, to this blue class, I know that I have crossed several walls in the middle. So therefore, in principle, I should expect some part of my module to change. But maybe I have removed one part, and then I have put it in another part. I think, for instance, of a mag. If you have mag, you have the cylinder and you have the handle. Maybe you have removed the handle and put the handle in another place. But then the mag is isomorphic. You just have to rotate it back and you get an isomorphism. So is it possible that you get two different of these isomorphism, different chambers that in principle are different? In principle, you have made some modification in the model going from one to another. But is it possible that these two are isomorphic for another reason? This is a P3, this is another P3. I have made no change from the point of view of the geometry. And the thing is that we have some answer for that. First of all, we know that if two chambers share a wall, the change is through a flip-flop. So there's actually a change. The thing is that, as I said, maybe this flip-flop is remove this and put it in another place. So nothing might happen. So what can we say about this isomorphism? Well, first of all, there's a Torelli theorem. In all this picture has spoken about a curve with some points. Well, this is critical. If two moduli spaces are isomorphic, that means that the ranks are the same and the curves, the pointed curves, must be isomorphic. And given that curve, we can prove that there's actually a finite number of chambers giving a finite number of isomorphism classes of these objects. And even there, we know how to transform, how they transform. So, as we say, suppose here now that we have fixed the curve on the points, but we might have changed the stability conditions and even the determinants, even the degrees. Is it possible that two of these are isomorphic? The answer is yes. There are 4 what we call basic transformations, allowing us to transform a stable parabolic vector bundle into an unstable parabolic vector bundle with another stability condition. The four transformations are natural transformations of this type of objects. First of all, if you have a vector bundle and you get an automorphism of the curve that respects the set of points, if you pull back, you get another vector bundle with a filtration of the set of points. So then you get another parabolic vector bundle. If this has a determinant chi, then this has a determinant pullback of chi. And if this sigma has permuted the points, then you just need to permute the stability condition in the same way, and then the stability condition is preserved. If you get a line bundle and you get a parabolic vector bundle, if you tensor by it, then you get another parabolic vector bundle of the same curve. The determinant gets multiplied by L to the R, and then as this doesn't change the parabolic structure in any way, the stability condition is preserved. Then you can compute the parabolic dual. Not getting much in details here, but the parabolic dual also transforms the determinant in a certain way. And here, as when you dualize, you revert the inclusions in a set, in a way, then it is natural that the stability condition is simply reverted. So if you get weights alpha 1, alpha 2, alpha r, then you get weights alpha r minus 1, etc., etc. It's just that you get to revert it. So you get 1 minus alpha r, 1 minus alpha r minus 1, 1 minus, etc., going down to 0. If you renormalize, instead of 1 minus the weights, you get the top weight minus the weights. So you end up renormalizing and the first one being 0. But then this reverses the weights. And finally, there's an interesting one, which is the Higgs transformations. Higgs transformation, Higgs modification, corresponds to using the parabolic filtration to perform an elementary modification at a parabolic point of an element. I'm not going to get into much detail here also. You just need to know that this also transforms like the determinant. Roughly speaking, they decrease the degree by 1. You can modify it essentially by O of minus 1 point, at this point, the parabolic point. And then what this does on the weights and is preserved is that this rotates the parabolic structure. And then the weights rotate in a certain way. You rotate and renormalize. So if you get alpha 1, alpha 2, alpha r, the alpha 1 goes to the end, and then everything rotates accordingly, and then this corresponds to just renormalizing it back to the 0, 1 interval. As I said, the corresponding formulas are not very important. What is important is that you get a correspondence. If you start with a stable quasi-parabolic vector bundle, which is alpha stable, that means it's stable for the stability condition alpha, and you modify alpha through these transformations, then you obtain that T of E dot is a T of alpha stable quasi-parabolic vector. And the determinants transform accordingly. So then what this gives are isomorphisms between modular spaces. And what we proved by indices, with Thomas, is that every possible existing isomorphism between two different modular spaces of parabolic vector bundles must be one of these basic transformations. And as they need to preserve the stability conditions, then they need to be precisely the basic transformations such that they send the determinant to the determinant, they preserve the determinant, they preserve the degree, and they preserve the stability condition. That means these numerical integral vectors that we described previously must be preserved. Okay, so this is good because then we have a full classification through these integral conditions about all the possible stability chambers, and we know all the possible non-trivial isomorphisms that exist between them that do not correspond to just being the same chamber, right? The problem, this comes out of hand very, very quickly. In fact, I can tell you that I just showed the 5 little examples I showed you are the only ones that I'm capable of showing. Let me show you this, because this might make things I don't know here. This little table right here corresponds to the number of stability walls that happen in a modular space of n parabolic points and r elements. If you look here, okay, these are the samples that we looked at. Okay, these 3, one division per moduli. Here are 3 divisions, 4 divisions. This is the simplex side thing. Okay, if I start moving here, the next small example has already 12 stability walls in a very non-trivial way. But if you start moving down here, you will see numbers like 10 to the 6 in the order of millions, 10 to the 10, 10 to the 15, 10 to the 54 right here. And if you look at how it grows very fast. Even the closest examples right here. Okay, if I have only one parabolic point, things do not behave so badly. But even if I have only rank 2, for rank 2, they start to increase the number of parabolic points. This gets out of hand in the millions very big. Even if I fix something like rank 2, I end up here in the millions right here. This, yep.
Okay, so the natural question, can I interrupt?
Yeah.
Natural question. One is that, are you going to tell us that you found some kind of relation when you fix the rank and then in the numbers that are with different points and so on? Okay, thank you.
Yes. Well, I can actually give you the explicit expression for this.
I'm looking forward to it. Thank you.
Yeah. So the thing is that, and this is the key point. So first of all, this is highly non-trivial. So as you start increasing the rank or the number of points, and this is just the number of walks. This is the number of walks. So now think about the number of chambers. In fact, I may give you a glimpse on the feature. Oh, sorry, this is not. No, wait, sorry. Yeah, I can give you a glimpse on the number of chambers. This is not complete for the reasons that you might see in a second. Okay, this is the example that I gave you right here. 1, 2, 2, 5. This is the hypercube cat 5. Okay, if I move one place to the right, this is already 720 chambers. But if I move a little bit more, now I'm in the order of the 4 millions. I'm in the order of 10 to the 8 here. And this is just 3 points rank 4. 3 points rank 4, there are already 5.7 times 10 to the 8 different chambers in this model space. And this gets out of hand very quickly. I can move around here and understand what's happening, but you rapidly go in the hundreds, thousands, or millions of chambers, even if you move slightly. So this raises the question: how can I find patterns in this data if I'm only capable of seeing clearly 5 examples? And even and those 5 examples are so simple that I cannot see any structure. Because those are so simple, are the most basic examples in which I cannot see any meaningful pattern in the data, because the patterns that arise there are particular to those very small cases. So I cannot see, for example, if there's any relation between, I don't know, maybe there are numerical conditions and the common factors between the number of points and the rank do something, the degree does something. Maybe I need to take into account the prime decomposition of the ranks. Spoiler alert, you need to do so. And I cannot do so if the ranks are 2, 3, 4. Right? So, what did we do? Okay, trying to do it by brute force, just computing these numerical invariants that I described about these integral sequences of elements is invalid. You can do it for the examples that I told you, but the size of this integral vector rises hyper exponentially, as I said, and then you end up very fast out of memory and out of computational time, even in the most basic example. So it's impossible to do so. So what we did is we involved another type of computational tools, borrowing a little bit from machine learning techniques. So we involved a combination of Monte Carlo methods, binary decision trees, and some computational and convex geometry to do what we call polypart. So how does polypart work? In essence, it is very simple. You start with a polytope, which is this syntax in blue in this case, and a set of hyperplanes, which are these red, green, gray ones. Okay? So you start with a set of hyperplanes, and then you will find one of them. In principle, you can suppose that it's random. In practice, you try to equilibrate that the halves that you are going to cut through are more or less equilibrated in a information theoretical sense. But then you cut, and then you form 2 polytopes, one of each side. The thing is that now, maybe some of these hyperplanes do not cut anymore one of the sizes. So then you can simply remove them from the speculation. So then, for instance, you use this hyperplane, you cut here, suppose that you are with the rear part, then maybe this red part here, if you look at this picture maybe, this red plane here does not cut the rear part of this arrangement. So then you can simply remove it. And on the front part, the blue one does not card, so the green one, sorry, does not card this front blue part here. So then you can remove it. So then you can recursively now go through this tree of simplexes, of polydrops, cutting each of determining for each piece which hyperplanes are still alive for your problem, and then recursively cut in again, selecting one of them. In this case, there's only one to consider, so you can only calculate this. And then you get the blue part remaining here, which is another polyton. You cut it by this remaining one, and then you get the two pieces. Here, you have run out of planes to cut, so these are leaves. These chambers are full chambers. You cannot cut them anymore. If you do this recursively over this whole tree, and you run through this tree, now, okay, this is the mathematically this seems simple. Think about the engineering implications of this. This number of hyperplanes is as high as the numbers that I told you before. This polytope is a polytope in D dimensions. Cutting a polytope is non-trivial. This engineering has its complications, but my student Sergio is a very great programmer, and he went through this and made a very optimal code, being able to do this very, very fast. And then what happens is that by the end, when you arrive at is a tree. You get a binary decision tree. The selection of the hyperplane gives you a condition. Points such that when you evaluate the hyperplane, give you a positive number, goes to one of the arrows. The numbers that get negative goes to the other, and the numbers that go to 0 are non-generic parabolic weights, and you discard. You might also classify them, but then for this work, we're going to consider also the smooth modular spaces in which the stability conditions are generic. Therefore, we will discard the points which are just on stability one. And therefore, you get both conditions. And then, for instance, what the algorithm does is it constrains this full tree. And if you go through the leaves, you enumerate all the chambers. Then you can also find in the algorithm a way to obtain a representative of one of those, the centroid namely. And if you get another point in the original polytope, then you can go through this transforms to a decision tree. So then you have a finite number of decisions, because if you go through this tree, you are selecting. It is like the who is who game. Does this do this weight? Are these weights on the left or on the right of this hyperplane? Okay. Are these weights on the left or right? Okay. So the magic here happens if you choose this randomly. This is not so interesting, but if you choose this, if you make this choice of what to cut at what moment, more or less in a reasonable way, you can make it so that without a much computational overcost, you can make this decision tree as balanced as possible. And therefore, you can very fast probe against a given parabolic stability condition and see where it belongs and enumerate everything in a very compact tree. And by doing so is how we obtain this. I have to say that not all this has been computed through this method. Only the triangle on the top part has been computed to this method. There's a point in which, of course, you cannot handle a 10 to the 54 size array of hyperplanes and chambers and a tree of that size in dimension. The dimension of the modular space of 20 points, rank 11, this is huge, okay? But we were able to obtain part of it, and then we started discussing. Okay, so we have these hyperplanes. Now, how can we, can we enumerate? Can we find a structure in this set of numbers? And this is the interesting part. We didn't find first a structure in this data from the mathematical point of view. But my student did find patterns in the data using machine learning techniques. So what he did was, okay, now I have data. I can try to find patterns in some of these data. So for instance, he started with this rank 2 column, which is the smallest one, the one in which we have more data, which is the smallest. Okay? And he tried to see a pattern. And he saw, he ran some numerical analysis there and tried to find some symbolic regression techniques to try to find a closed formula for those numbers. And he found it. He found that these numbers satisfy some exponential rule with some additional factor that's not so trivial to see at first glance. But I mean, these are more or less powers of 2. You're more or less doubling. Not going something, but you're more or less doubling, right? So he found a way to actually find a thing here. Okay, so we are dealing with exponentials. So then he tried to apply, once he saw the pattern here, he tried to apply the same pattern to the next column, rank 3. And then he, now that he saw what the rank 2 looked like symbolically perfectly, he reduced the search space so that he could try to look at something similar for rank 3. And then he found something. Then he tried to apply that to rank 4, but rank 4 didn't work. It was nothing like rank 3. But you know what? Rank 5 did work with the same technique. Okay, so what do 2, 3, 5 have in common? Prime numbers. So then, okay, why is it being so hard for us to find a common pattern in all this? Because there's no common pattern for all ranks. It depends in some way on the factor decomposition of the ranks. And then there's no easy regularity. Like for instance, when we tried to look at the horizontal lines, it was crazy difficult to find some pattern. But then, okay, it seems like for prime numbers, okay, so let's try for 7, like it works. Definitely, it works. So then we have some conjectural formula for the prime factors. Okay, so now that we know that the primes are involved some way and the factor decomposition is involved some way, we can try to find, instead of trying to look at 4 completely, let's try to split. Let's try to find, because here in the formulas, it depends on some rank are primes and degrees the rank. Okay, let's try to split and filter out and segregate our data by R prime and by the coprimality or the divisions and congruencies between these different. So then from this single column, you get a lot of columns. And then we start seeing patterns. Like, okay, so not all the congruencies types get something, for instance. So actually, there must be some numerical reasons for some congruencies to be empty. And actually, we were able to prove that they were this. Then we were finding that the ones that were not empty were more or less evenly distributed, which was non-trivial. So can we prove that? Okay, yes, we can. There's a way we can prove that these are non-empty and non-trivial. Then we can try to find which are the beans that are non-empty. And there are some numerical conditioning. We try to analyze and say, okay, so maybe this has to do with these coprimalities and these non-coprimalities. And we did. Then step by step, each time we discover one more pattern, we could redo this analysis by filtering down and segregating the data in a way that presented everything non-trivial, right? And we ended up with an actual formula. I'm not going to present the full formula here, but just for you to know, for instance, there was a very non-trivial contribution of the common factors of the rank and the rank of the subbundle here. And this looks something like this. So there's a sum of pieces, and each piece is between 2 elements that rise as combinatorial numbers multiplied by a certain linear factor, but with a correction term that needs to be accounted for that takes into account the common prime factor between the two. That's why when the ranks were prime, this term is always 1, and this simplified to a polynomial exponential type of formula, easier to find. When it is not, you need to take into account the common factors, and it's a sum of polynomial exponential families depending on the factors on the rank, which is highly non-trivial. But the thing is that we were able to find. We were able, by doing this combinatorial exploration, we were able to actually find these results. And then we were able to find actual more or less nice bands, allowing to actually complete this full table. Okay, but now this is the number of walls. What happens with the number of chambers? As I said, this rises fast, but there was a catch here. Okay, so I said that here the algorithm allows us to take this or construct this full binary decision tree that allows you to search and decide where does a given alpha lie on. But it doesn't only do that, but also you can apply these basic transformations to the points. So if you start at the chamber and want to see the automorphism, we can do the following. We start with an automorphism with a chamber with an alpha. We apply the basic transformations, the possible basic transformations to it. And then the problem would be that maybe, so it's not enough for the automorphism to lie, it's not necessary for the automorphism to lie on the same exact alpha to have an automorphism. If you apply a transformation and you lie in a different alpha, but in the same chamber, you do get an automorphism. So it is very complicated to actually classify all the possible automorphisms, all the automorphism group, or the exact automorphism group of an element, because even if you have the explicit equations of the chambers and the explicit equations of the transformations, you need to actually solve a highly non-trivial optimization problem or system of inequalities to see if you actually ended up in the same chamber. Polypart does that for us. You can take an alpha, compute the transformation through a T, through a basic transformation, and then when you get the endpoint, you just go through the binary decision tree, and you can see where it lands. If you landed on the same original chamber, you are good. You have an automorphism. If it landed in a different chamber, you have a non-trivial isomorphism between two different parabolic chambers. Then we run that, and surprise, surprise, you have here the numbers. You go down to here. Let me put one by side by side comparison. This is the number of different parabolic chambers. This is the number of different actual non-trivial isomorphism, different isomorphism classes. So basically, you have things like here you have more than 10 million parabolic stability chambers. Only 270 are actually non-isomorphic modular spaces. Here, the numbers might be smaller, but you see that here there are a lot of non-isomorphic. Here is clear also 4 million parabolic chambers with N4 and N3. Here you go down to 4,000. So it seems like even if you have a very complex stability space with a huge number of isomorphism, a huge number of parabolic stabilities, only a few of them are actually non-isomorphic. So most of what could be automorphisms actually end up being non-trivial isomorphism between different things. So what do we get out of this? Okay, we start analyzing the data. This is actually, by the way, these are data sets that are publicly available. We publish them. So you can look at exactly at all these isomorphisms between the moduli and all these automorphisms of the moduli. But then the thing is the following. The automorphism group, we know that it splits in a shortest sequence of groups. Okay, so all possible automorphisms of the curve that fixes the parabolic points and act on the moduli, but they act trivially on the stability conditions. Also, tensor invariant bundle acts on the moduli, but acts trivially on the stability conditions. But the remainder, so then the automorphism group splits as two halves. First, things that act trivially on the parabolic stability space, but act non-trivially on the moduli, and then things that actually act on both, act on the stability space non-trivially and on the moduli. So this action reduces to permuting the points. The action on the stability space is a permutation of points, maybe duality, and maybe the Higgs transformations, which rotate the points, right? So permute the points, rotate the weights in the points, or dualize, which inverts the direction of the change, right? And the thing is that we found that there are a lot of unsuitable combinations that you cannot obtain. When you look at the data, first, when we started analyzing this problem with Thomas, we thought that all of these transformations were available, and they are. For every one of these basic transformations, there exists a modular space of parabolic vector bundles, admitting them as automorphisms. In fact, there exists a choice of stability conditions that is fixed by all of these, and such that the group of automorphisms of this modular space is the full group of basic transformations. The problem is that this modular space is highly non-singular. It's highly singular. It's a highly non-trivial, highly non-generic set of parabolic weights. So what happens with the generic ones? And this is where the surprise came from the data. We saw that most of the possible choices that we could make were unavailable. They were not found in the data. So we started looking for values. So what can we find? Well, first, if we have that a lot of, so the basic transformations must play two different roles that must be combined. When you consider a basic transformation, only two things can happen. You start with a parabolic weight, you apply the basic transformation, either it lands on the same chamber or in another. So either it becomes an automorphism or it becomes an isomorphism with another chamber. If we see that the number of non-isomorphic, because how do you find the non-isomorphic ones? You have a graph for each, you have a point for each parabolic chamber and an arrow between two parabolic chambers for each transformation. The connected components of this graph, which is a groupoid actually, are the isomorphism classes of the moduli, right? So if we find that there are very few isomorphism classes, that means that each class is very big. That means that for each parabolic point, the transformations that either land on the same thing or land on another, most of them land on another, right? In other words, it must be very difficult for these parabolic basic transformations to land back in the same stability chamber if the stability chamber is generic. And then we started looking for patterns, and we found some. For instance, duality was never there. In no generic parabolic chamber, you could find any automorphism involving duality. Not just that the duality itself is not, it's just that no basic transformation with duality was ever an automorphism of one of these things. And there was a very surprise. But then we started looking at why. We started doing experiments with actual points in high dimension, and we found why. There was some inversion of the space and some orientation problems, making duality never become an automorphism of the whole space. But then also there were some problems with Higgs, because most of the Higgs were not present there either. And even with permutations, most of the permutations were not present there. It was very scarce. And then we were actually able to find explicit conditions. And we were able to find what are the conditions that you need to put on the permutations and the Higgs so that you actually get an automorphism of some modular space. And this comes, there are a couple of things which are very easy to consider. First, when you consider the duality, you can never use it. And second, the Higgs, the rank needs to divide the total Higgs. That means each Higgs is a rotation. If you sum the steps of all the rotations, that needs to be a multiple of the rank. If it is not, then you're done. And this type of non-coprimality conditions or coprimality conditions, you may think of them as something similar for the people who work with vector bundles. You know that it is very different. The modular space of vector bundles with rank and degree, coprime or non-coprime, they are very different. So why don't we have, or why wouldn't we expect this type of coprimality conditions in the parabolic case? Okay, you don't expect them because the parabolic weights are real numbers. So how would you get coprimality conditions if your stability conditions are real? Okay, here's the catch. You get them because, yes, the coprimality, so the parabolic weights are real, but the chamber structure is discrete. And the chamber structure depends on numerical conditions that are integral. And those integral rational conditions involve number theoretical implications on the choices of the automorphisms. So then what happens is that you can find an actual very explicit closed set of Diophantine equations that describe precisely which transformations are automorphisms of some modular space and which are never automorphisms on any modular space. Let me give you an example, a concrete example, in one very simple case, in which suppose that D is a generic set of points and that the rank is prime, so that you don't get very complicated numerical equivalents. Then the automorphisms of the moduli only have two possible components. Either they are tensorizations composed with Higgs, no permutations, no duality. And then the Higgs must satisfy a certain very simple numerical condition. The rank needs to divide the total divisor H. And this is because we need the tensorization to be our root of O of X. So then this needs to be a multiple of R for this to exist in as a remainder. And then there needs to exist some point for which the Higgs does not act. That means the only automorphisms comes from actions of Higgs and actions of Higgs, really, because the tensorization is only there to go back to the same degree, really. But it needs to be tensorizations, Higgs, such that at least one parabolic point is never touched by the automorphism. And then if you find one of them and you find one of these T's, if this doesn't happen, this automorphism is never an automorphism of modular space. Even if you do find it, then if some of these transformations are automorphisms of a certain modular space, then you can actually, as a consequence, describe the full automorphism of this modular space. The modular spaces in this setup, R prime and generic parabolic weights have the following explicit structure. They are there must be some subdivisor, so inside the divisor of parabolic bundle there may be some side divisor of points which are fully fixed. by all the automorphisms. That means that you are performing Higgs that are trivial on those on that set of points, and such that on the rest they sum a multiple of R so that there exists a square root of this thing. And then the full automorphism group is just a semi-direct product of the R torsion of the Jacobian tensor by power of a torsion element set over R set to some power depending on the difference between the number of parabolic points and the number of fixed parabolic points. And this is fully split. You have a full description of it. Okay, this is the first. I'm running a bit out of time, but very quickly, let me rapidly give you a glimpse of the second packet, because as I said, all of this is automatic. The first packet I described does these computations on the parabolic structure for you. So this experimentation is done through these packets, and it could be extended to other modular spaces. But we did it for that. And then we added a second package which has to do with motivic expressions. So here we have the motives package. Again, this is a Python package. And this is a computer algebra system for computing expressions in lambda rings. And arbitrary abstract lambda rings, in particular, on the Grothendieck ring of models. Why is this important for modular spaces? How do you use it? Okay, first, you can make computation simplifications of modulic expressions. For example, you have a modular space of vector bundles, you can compute the motive. The motive is encoded in the package. The package includes the typical and in fact state-of-the-art of the existing formulas for the most commonly used modular spaces of bundles, stacks, groups, stacks, etc. And you can just out of the box compute these things. You can simplify them. You can explore and verify conjectures involving these equations. Like for instance, if you have two different formulas for a thing, or you want to split a formula, or you want to obtain the compositions, for instance. This is what we're doing right now with Jacob and Thomas. You have an expression of a motivic expression for a certain module. You want to find non-trivial decompositions of this expression of a certain particular form. And then what you can do is this package allows you to do all the motivic computations abstractly. For instance, regardless of the curve, for instance, you have model space of vector bundles over a curve, you can instantiate an abstract curve of genus G, and then compute everything with regard to that abstract curve of genus G. You don't need to actually make the explicit algebraic constructions of the corresponding show motifs or whatever, and play concretely with the equations of some curve, but rather you can play with an arbitrary abstract curve and make everything regarding to the cohomology or the properties of that curve, whatever they are in abstract. Okay? So what did we apply it to? Modular spaces of twisted Higgs bundles. Very quickly, twisted Higgs bundle is a vector bundle together with a Higgs field, which is a map from E to E tensor by L. That means in an L tensor endomorphism of the bundle. And these modular spaces are relevant, for instance, when you consider, related to the previous modular spaces, when you consider parabolic or logarithmic Higgs modular spaces, disappear in place. Also, they have to do with the algebraics. When you consider modular space of the algebraics, you can prove that the homology of the modular space of the algebraic connections is the same as the homology of these kinds of elements. Well, that means that it might make sense to try to compute the motives to know the full topology of these guys. And then we have the following problem. Back in 2024, and the Oliver and I managed to compute an explicit equation for these motives. We have a method for computing or for reducing certain motives of moduli of chain bundles, the full motive of the modular space. And then for run 1, 2, and 3, you can explicitly obtain an explicit formula, which is a certain sum of pieces. And this sum of pieces have to do with a certain lambda structure, which in this case comes from the symmetric powers of manifolds. So you have a variety and a variety. You consider the symmetric powers of the variety. That means variety times variety divided by the symmetric product. Then this lambda operation makes the Grothendieck group of motifs lambda ring. And then you can express this variety as a certain sum of pieces, and all these pieces are symmetric powers in a certain of a certain right? Okay, so this is okay. It's more seems more or less complicated, but in reality, it's just a sum of pieces. It's nothing more. You're just having certain blocks corresponding to certain cases. These sums have to do with the stability conditions again, and then you compute all these sums. Each piece is very simple, but you compute all the sum, you are done. But then, after we published the first draft of this, Sergei Mozgovoi made us realize that he had published some time ago in the 2012 a paper in which he included a conjectural formula for this, based on motivic ADHM equations coming from string theoretical arguments. This was not a problem because it relied on some string theoretical arguments that made it not a theorem but rather still a conjecture. But it was a strongly supported conjecture. The problem is the equation that he sent us and the equation we saw in his paper had nothing to do with ours. Now, in our case, as I said, it's a sum of pieces. In his case, this was some theta motivic equation involving a certain generating series of zeta motives. Then you have a probabilistic logarithm of the sequence. Then you roll everything back into another generating sequence, and that generating sequence ends up being a factor you to adjust with some dimensions of the actual body of the model space. And then the question was, okay, are these two equal? Because we have a conjectural equation which works in every round, but it's still conjectural. It's based on stringy arguments. Then you have a geometrically based decomposition in pieces that we know is a theorem, but they look nothing alike. So how can you compare them? So that's what our system comes into play. What our equations do is they are able to transform every pair or every lambda ring expression as complex as this into a certain polynomial in a finite set of lambda ring generators. In this case, for modular spaces of this type, which are generated, so in both cases, all these expressions were generated by zeta functions of a curve, of the base curve in which it's played. And here it's the same; they are generated by symmetric powers of the curve. So at the end, everything depends only in both expressions. They depend all on the left-shift motive and symmetric powers of algebraic curves. If that's the case, what the algorithm does is convert any expression depending on those elements as a polynomial in the symmetric powers of not the curve, but a certain Hodge, certain show decomposition of the curve. But there's a finite number of generators. I'm not going to get into the details, but the thing is that this is not only a thing in multi-bit theory, but there is a problem in lambda ring theory. If you have a lambda ring, it's a ring together with an exponential operation, which you can find lambda powers. The typical example you can think of is the integers. Instead of having the usual power x to the n, you can have the divided power x over n. And then if you put that, these binomial operations satisfy a certain convolution rule in which the power of a sum splits as the convolution of the lambdas of the elements. And then if this is satisfied, we say that this exponential operation is a lambda structure for the ring. The thing is that this is not the only ring where this exists. For instance, in varieties, if you have the K0, so you have the bundles, the symmetric powers of a vector bundle and the exterior powers of a vector bundle satisfy similar relations. And for our interest, in motives, the symmetric powers of a scheme also induce or can be extended to a lambda ring structure on the Grothendieck ring of varieties, and also in the Grothendieck ring of the Shaw ring of models. The thing is that this is okay, but what if we have iterated things? For instance, what if we have a lambda 3 of x times y or a lambda 3 of a lambda 2 of x? In these equations, you say how lambda operates on sums, but how do you compose lambdas, or how do you create the products? If you don't know that, you cannot expand fully expressions. The thing is that you can consider some certain kinds of lambda rings, which are what's called special, in which you have additional polynomial relations regarding how do you operate on products and on composition of lambdas. The problem that we have is that, okay, for instance, integers set is special, but the ring of motives is not. Fortunately, the opposite structure, whatever that means, I'm not getting into that, of this is special. So what happens is that, long story short, we found a way, we found an algorithm capable of simplifying every, so if you have a lambda ring such that the opposite lambda ring is special, like the motives one, or if it itself is special, that's great. But if it is not, even if it's not special and the opposite is special, which is the complicated situation we're looking at, we can still find an algorithm capable of simplifying every expression into a certain polynomial in lambda powers. Okay, so I'm running out of time, so I'm not gonna give much details on this. Just for you to know that if you have any motivic expression, this simplifies it into a certain polynomial. It can be a very large polynomial, but it's essentially a polynomial. So then you have two very, and this polynomial is unique. There's a unique polynomial satisfying certain relations that corresponds to a given expression. So if you have two different motivic expressions on the same set of generators, for instance, corresponding to the same modular space depending on a curve, and both expressions depend only on the curve, then you can go to the left expression, apply this algorithm, take a polynomial out of it, go to the second expression, apply this algorithm, take a polynomial out of it, subtract, and this will give 0. If it's not 0, the expressions are guaranteed to be different. If it is 0, the expressions are guaranteed and proven to be. Okay, this done globally would allow you to check or verify certain conjectures. Like for instance, we were able to verify the Moscow conjecture. But the interesting thing is not just checking the full thing, but rather doing it part by part. The interesting part is that when you are working on proving it by hand, there are certain steps in which you are, for instance, making some complicated substitution, or you are making some work on it. Then being able to actually check that your last equation is actually correct, and you didn't make any mistake, or being able to autocorrect certain exponents that are wrong, etc., that's the powerful thing. That way, working on the problem, you can have a companion working with you and checking at the same time all your computations step by step. For instance, if you have a conjecture like, okay, this equation is equal to this because this part is equal to this part, and this part is equal to that part. Then what you can do is, okay, let's check it. Let's subtract these two, compute, done. They're equal, therefore the other two are equal. Or let me split this as a sum. Each of these summands a positive element. Let's compute it. Blah, blah, blah. These are dimensionally sound. We compute, obtain the polynomial, and compute all the invariants from. And as I said, this package generically is for lambda rings, so you can use this for any lambda ring that you wish, for instance, for symmetric polynomials, or for K0 theory, or for whatever. It's specialized for lambda rings of geometries, and in that case, it contains out of the box all the motivic theory for complex algebraic curves, Jacobians of these curves, symmetrical alternative products, model space of vector bundles and their stacks, model space of altruistic Higgs bundles, model space of chain bundles, variation post structure, algebraic groups, a stack of bundles and principal G bundles, and also typical classifying stacks and groups B, G, and G for the classical groups. And we are adding here, there are a couple of more things. For instance, we just added Grassmannians, for instance, also typical. So we are trying to add most known equational equations for known motifs of this kind of common daily use elements. So you can just out of the box say, okay, what's the motif of vibration, Grassmannian vibration, or a flat vibration over my modular space of parabolic vector bundles. You can just out of those and compare it with other guys. Using that, our result was first to be able to verify most global conjectural formula for any curve of genus up to 12, up to 18 and for any twisting, I mean number of parabolic points up to 20, and rank up to 3, which is where the equation with Andre was found. And then using this copilot, we were able to actually prove that the equation is fully true for any genus in rank. And we are currently trying to prove rank 3. We are advancing in this, and we were able to make some great advances. We are not done that. We expect to be able to prove it also for the rank 2 and rank 3, which is the ones for which the equation with Andre Oliveira work. We expect to be able to also extend that to higher ranks in the future, but we are doing more of machine learning. So that's it. Thank you very much for your attention. Here you have the paper on the lambda rings structures, on the motifs. And here you have the CMO GitHub, where you can find these two packages and other packages with similar type of behavior that I didn't speak about. But for instance, you can find here all the documentation and code of this. Thank you very much.
Well, thank you very much, David. Any questions?
In the previous theory, did you study which are the possible groups in G alpha? I mean, if I give
you mean in the here?
Yeah. Mm-hmm. For example, if I give you a concrete, for example, finite group, can you decide whether it's isomorphic to some G alpha?
Yes. Almost fully. Yes. But I mean, okay, so these conditions are fully explicit, but they rely on the resolution of some Diophantine equation. So when you solve, so what are the automorphism groups? The automorphism groups are the transformations which are solutions to that Diophantine equation. The Diophantine equation is fully explicit, but it is complex because there's a, okay, so in the case of vector bundles, there are only two parameters, rank and degree. But here, there are a lot of interactions. Each Hecke gives you a numerical invariant, which is the step of the Hecke over each parabolic point. So you have as many parameters as points in your parabolic moduli, and you have as many codimensional, so as many. So you have to compute certain great common divisors with respect to the rank of every step of every Hecke, and there are some non-trivial interaction between the orbits of the. Because okay, sorry, I went ahead of myself. So suppose that you have a given modular space. You go with the automorphism group. This automorphism group, we know it is made of combinations, so duality is out of the picture. The tensoring only adds a semi-direct product with a Jacobian, or the torsion of the Jacobian. In particular, if your finite group does not contain, is never or cannot be realized as a semi-direct product of some torsion Jacobian of some algebraic curve, you're done. That's not so trivial to characterize, by the way. But say that you can find an actual, so you are dealing with, you have the curve, you have the Jacobian, and you're wondering the remaining parts. So that means what are the finite groups which are extensions of the torsion of the Jacobian of a curve that are coming from automorphisms of one of these. Okay, well, the answer is trivial. All the Heckes transform additively. So you have a type of lattice. Now, this type of lattice, in this case, is very simple. It's just a top element. But in the more complicated case, you have some complementarity conditions, and you might have union of components of these guys. And depending on your modular space, you are in a different component with a different object. They are not as simple as this, but not much more complicated. What's complicated is the condition. That means you are not getting just R orbits of element. No, you are getting a little bit more complicated orbits, and you get a numerical condition on what the Hecke should look like, so that you get. So instead of getting the full set over R to the whatever, you are getting a lattice into that. So that lattice is an additive lattice, so the structure is not so complicated. The thing is seeing if that lattice has the same type of relations that you want for your representation of your finite group. and then that corresponds to solving certain numerical conditions. And in fact, it's a system of a couple of it's just two Diophantine equations. It's a system of two Diophantine equations. One is a linear affine Diophantine equation, and the other is in incongruous modular, and the other is a divisibility condition. It's just that certain great common divisor of some things is less than r. Sorry, the least common multiple of a certain set of great common divisors is less than r. So if these two are compatible, then you have modulus. You can find a modular space such that the automorphism group is precisely that group. So yeah, it's very explicit. And in fact, for small cases, we have the full enumeration. For small modular spaces, that means for rank less than 5 or 6 and number of points less than 4 or 5. The triangle I showed you that they have all the data. For that triangle, you can find the full description explicit for every modular space and the full automorphism group with explicit generators. So you have the exact enumeration of everything. So you can actually check, okay, so does this automorphism group is the modular space, is the automorphism group of a modular space of rank less than whatever vector one is? Okay, so I go to the list and I say, okay, it's in the list. Yes or no? If it is, done. If not, it's not. Yeah.
That we will kidnap you and after and ask you more questions. So thanks, David, again for this talk.
Thank you very much.